This is going to be section 10.2. And we continue with our analysis of possible ideas to prove a fundamental theorem of arithmetic in an integral domain. So far, we considered a proof of the fundamental theorem of arithmetic in Euclidean domains. We directly generalized from our proofs for integers and for polynomials with coefficients in a field. Now we introduce another class of integral domains and another idea which may, and actually does, lead to the proof of the fundamental theorem of arithmetic. That is another common property of the ring of integers and the ring of polynomials with coefficients in a field, which we will capture with this idea. Here is the definition. So that's about PID, which is principal ideal domain, and the definition is a PID is an integral domain in which every ideal is principal. Oh, let me recall that principal ideal A, this is a notation for principal ideal generated by an element A, is the set AR R in our ring, in our domain. It is easy to see, we have a criterion that this is an ideal, so for A, an element of R, this is principal ideal. Well, let me write it here so that it's not confusing. This is a principal ideal generated by an element A in our ring. We will see in a moment that both the ring of integers and the ring of polynomials we discussed earlier are PID. Not every ideal is principal, by the way, so not a principal ideal is the ideal generated by two polynomials, 2 and x, as an ideal in the ring of polynomials with integer coefficients. 2x, by definition, ideal generated by these two elements. They are both polynomials with integral coefficients. This one, 2, is of degree 0, x is of degree 1, and this is as a set to f plus x g for f and g, all polynomials in z of x. The ideal generated by two elements, not one element, is not a principal ideal. Just an example of not a principal ideal. So this ring is an integral domain which is not a principal ideal domain. However, let us consider principal ideal domains, and let me first convince you that this is really a more general notion than Euclidean domain. This is theorem 10.8 from the book, which claims that every PID, other way around, every Euclidean domain is PID, is a PID, to make it clearer. I will give only the idea of proof. You will look for details in the textbook. Idea of the proof we consider I an ideal in R. R a Euclidean domain, and we want to prove that this ideal is principal. We consider all the set of all delta. Delta R is an Euclidean domain, so it is supplied with the function delta. Delta of I for all I in the ideal, except 0, which is definitely in the ideal, but does not have delta of I. This is a set of non-negative integers and therefore has a minimum element. Thus, say, call it B, meaning delta of B is smaller or equal than delta of I for all I in the ideal except 0. Now, the claim is that this is the generator. I is a principal ideal generated by B. Well, the proof of this claim, you will look it up in the textbook. Well, the idea is that the division with remainder Euclid's lemma. R is a Euclidean domain. We divide with remainder by B and find that every element is divisible by B. That means that I is the set of all multiples of B. With the help of Euclid's lemma, proof 1 proves that B divides I for every I in the ideal I. This is a standard argument. We need to prove that the remainder is 0. The remainder is not 0, then delta of I was not a minimum. That is the outline. And now we want to prove that PID has the fundamental theorem of arithmetic. So this is theorem 1012, which says that the fundamental theorem of arithmetic holds true in every PID, principal ideal domain. The proof is based on a little bit different ideas, and therefore I will try to outline this proof. Towards the proof of the fundamental theory, I want to firstly remark that as soon as this theorem 1012 is proved, our old results about fundamental theorem or the fundamental theorem of arithmetic in the ring of integers and polynomials are proved immediately. They are Euclidean domains and therefore PID, and we are going to prove that in every PID the theorem is true. Thus, that offers a slightly different way to prove the fundamental theorem of arithmetic. In Euclidean domains, it is true because they are principal ideal domains, meaning every ideal in these rings is a principal ideal. That is not true in general. Towards the proof of theorem 1012, firstly, the first step is to translate divisibility into a relation between the principal ideals. So, because the condition is every ideal is principal, so we want to work with ideals, not elements. We want to speak about something, about some properties of ideals, not some properties of elements. So a translation of divisibilities into the language of principal ideals. It is very good that we do not need to care about every ideal, only about principal ideals. That is simpler. So instead of speaking about an element divides another element, we want a relation between ideals. Let me first make it clear for you how does it work. This is a recall. So we have an ideal A principal ideal is the set of all multiples of A. R is an element of our ring R, integral domain in this case, and another principal ideal B is the set of all multiples, say S. B for all S in R. Now, A divides B means B is a multiple of A, Ra. Means, in its turn, B is some multiple of A. All multiples of A are elements of this ideal. So that means that B is an element of the ideal A. This is an ideal. A principal ideal is, anyway, an ideal in the first place, so it has the absorption property. B is an element in A implies by the absorption property that SB is also in the ideal for any S in the ring. And that means that every element as B of the ideal B belongs to the ideal A. So that means ideal B as a set is a subset of ideal A. So what we found that the divisibility of elements of the generators is translated into a relation between ideals as sets. One is a subset of another one. That is a part of the following full statement. So that is how the following theorem is proved. Other statements are either trivial or consequences of this one or can be proved in the same way. So let A and B are elements of R. Recall, R is an integral domain throughout this chapter, so I will not write it every time. This is a running assumption. In chapter 10, R, the ring, is always assumed to be an integral domain. So we have the theorem claims that first, one ideal is a subset, may be equal, of another ideal if and only if B divides A. Here it is A divides B. B is a subset. B divides A. A is a subset of B. Second, they are equal as sets and therefore as ideals if and only if B divides A and A divides B. Yes, of course, if you have A is a subset or equal to B, B is a subset or equal to A simultaneously, then they are the same. 3. A is a proper subset not equal to of B if and only if B divides A, but A does not divide B. So more or less from the first argument which I showed to you, everything else follows immediately. This is a way to translate divisibilities into the language of principal ideals. Now, the fundamental theorem, which we want to prove, has two clauses: existence of a decomposition into primes and uniqueness. For the existence clause, of the fundamental theorem, of arithmetic, we want to avoid the situation of an infinite chain. the following situation. P1 divides A, and we write, this is any reducible, and we write A is A1, say A1. A1 is P1 A2. Now P2 divides A2, and we write A1 is P1, P2, A3. Now A3 is again divisible by something. P3 divides A3. All P's are irreducibles, and we have that A1, which we want to decompose into product of irreducibles, is P1, P2, P3, A4. We want this not to continue infinitely. We want that to stop. At the moment. If this continues infinitely, we are trying to make a decomposition which does not stop. So an infinite series of irreducible, an infinite collection of irreducibles divide A1. A1 will not have a finite decomposition into a product of irreducibles this way. Example 1 in the book provides for a situation when it doesn't stop. Shows this is an example of a situation when that does not stop and in the integral domain which the textbook denotes as QZ of X, these are polynomials with rational coefficients and integral constant term. No decomposition. Into a product of irreducibles exists, at least for some elements. No decomposition into a product of irreducibles exists means in this domain the fundamental theorem of arithmetics fails for this reason. For this reason. Existence fails. One needs to require that this does not happen. Here is a definition which requires, on the language of ideals, that such a thing does not happen. Definition: an integral domain we say that an integral domain satisfies the ascending chain condition. Which we'll write as ACC, ascending chain condition. On principal ideals, for any chain of ideals, A1 sits inside A2, sits inside or equal A3, and so further the nested chain may be infinite. The condition requires that there exists n such that from nth ideal on, they are all the same. The chain stabilizes. An is equal to an plus 1 equal an plus 2 and so further. So all of them from some point on, they are all equal. You may write it same condition as an is equal to ai as ideals for all I bigger or equal than n. This is simply a reformulation of this condition. So ACC means any chain of principal ideals, nested chain of principal ideals, stabilizes, and that ACC is always satisfied for the domains under consideration. That is the content of lemma 10.10. Every PID satisfies the ACC. the ascending chain condition. The proof is interesting on its own. It's slightly different from what we've done before, so I will present it here. So we start with such a chain. We want to prove it stabilizes. So we consider the union of all of them, union over I of all these ideals as sets. It is easy to check A in our integral domain, in our principal ideal domain. This is our R, is our PID, is an ideal the point is that what do you need to check? There was a criterion. The difference between any two elements is still an element of A. How do you check that? Take an element in the union. It is in the union for only one reason. It belongs to some of the ideals. Take another element. It also belongs to some of them, to these ideals. Take that with bigger index. Look there. Or also, if an element belongs to A3, it belongs to all further ideals. So take the biggest index. This is an ideal which contains both elements. Their difference belongs to the same ideal, therefore to the union. Another point of the criterion, multiple of any element is back in the ideal absorption property. Take any element of A. It is an element of A for only reason it belongs to some AI. It cannot be out of all of them. Then it is out of union. It belongs to some AI. You wanted to multiply it by an element of R. Multiply. You stay in that same ideal AI, therefore in the union. That's it. That is how easy it is to check with the union of this nested chain. The point is that it is nested. They all sit inside one another. Therefore, union is somehow a good way to write the biggest of them. In general, if it was not PID, that the biggest could not exist. But that was a chain of ideals, but union is an ideal, not one of them. In the case of R is a PID, principal ideal domain, this is an ideal, and that implies, since R is a PID, A, being an ideal, must be principal. Because any ideal in principal ideal domain is principal. A is a principal ideal means that A is generated by an element. Now, this element A So there exists for some element in the domain R. However, this element A belongs to A, therefore belongs to we can rewrite it. A is the union. The element belongs to the union of ideals, but this is union of nested ideals, so it must belong to what anyway, belonging to union, nested or not, it must belong to one of them. Thus A belongs to an for some n. That's it. Other further ideals cannot be bigger than that, because this is already their union. It follows that an plus 1, an plus 2, and so further, because this already contains A, so this ideal alone is already equal to the union of all of them. These were given to be bigger or equal, but cannot be strictly bigger, because A belongs to an and generates their union. So the ideal which contains A contains their union, or union of all these ideals. That's the ideas for the proof of this lemma. The book presents the proof a little bit more formally than I did it here. And this lemma implies that this sort of situation, when we cannot reach a finite decomposition, is avoided. So existence of factorization into a product of irreducibles the existence clause in the fundamental theorem of arithmetic for PID in theorem 1012 follows from that. With a more or less mundane argument. This is the kernel for existence. Now we can think existence is already proof. You will look details in the textbook, and we're in a position to prove a key lemma for the uniqueness. So for the uniqueness, key for the uniqueness in 1012, the fundamental theorem of arithmetic for PID. That as lemma 1011 in the book, the statement which is very familiar to us. This is same thing as theorem 1.5 in the case of Z. Theorem 4.12 2 in the case of polynomials with coefficients in a ring, or corollary 10.4 in the case of Euclidean domains. The lemma is formulated as follows. So let R be a PID, principal ideal domain, and let P, an element of R, be irreducible. Now P divides BC implies P divides one of the factors, or both. So from here, the uniqueness in the fundamental theorem is going to be proved. Let us prove this lemma. It will give us, this is the last step. After that, the argument becomes mundane. So we have to prove this lemma for PID, and we are done with the fundamental theorem of arithmetic in the principal ideal domains. So we assume P divides BC, and according to our translation into the language of ideals, this means that BC is a multiple of P, so it belongs to the principal ideal P. So BC belongs to P wanted P divides B, meaning B belongs to the ideal P, or C, or P divides C, C belongs to the ideal P. I hope that this looks familiar. What we want to say, that is, we want to say, we want to claim that the ideal P is prime. That was a definition of prime ideal. If product belongs to a prime ideal, it must be that one of the factors belongs to the prime ideal. At this point, we will prove a stronger statement. So P is prime will follow from P is maximum. It is not a good sign when a proof contains a non-equivalent statement. Every maximum ideal is prime. Every prime ideal may be maximum, maybe not. Every maximum ideal is prime was corollary 616. Every maximal ideal is prime. That happened because every field has an integral domain. Factor ring over a maximal ideal is a field. Factor ring over a prime ideal is an integral domain. Every maximal ideal is prime because every field is an integral domain. Overkill tells us that something is going wrongly with our concept. We will prove the theorem, but most probably, and this is indeed true, the fundamental theorem of arithmetic is going to be true not only in PID. This is not the best, most general setting. So let us continue. And now I'm going to prove that if an element is irreducible, then the principal ideal is prime in a PID. So assume for the sake of a contradiction, or even no, assume there is an ideal, but it's assume there is an intermediate ideal between the whole ring, our PID, and our ideal P. I, an ideal. P is the maximal by definition, means that I must be either P or the whole ring. We know that our domain R is a principal ideal domain. Thus, ideal R is principal. So since R is a PID, the definition was every ideal is principal. Whatever I is, it is an ideal. Thus, it must be principal. Thus, I must be principal. I is an ideal generated by some element D. Now, P sits inside D means, as we already know, that can be translated into D divides P. But P is given to be irreducible. That was the condition. The element is irreducible. Who can divide an irreducible element? But P is irreducible the only divisors are associates of P or units. Thus, D may be either unit in this case D is equal to R. All multiples of a unit contains 1. Unit is a divisor of 1. If an ideal contains 1, by absorption property, it contains all elements of R. Or D may be an associate of P. In this case, the ideal G is P. Cause associate divide P and P divides associate. They are the same up to multiplication by an invertible element, a unit. If the divisibilities go both ways, this is a subset of that, and this is an otherwise subset. So they must be equal, or you can take it as a clause of our translation from the language of divisibilities to the language of ideals. D is, this is the ideal I. And what we see that if there is an ideal in between our ideal P was irreducible, this is a principal ideal, every ideal here is principal, R is a principal ideal domain. If there is an intermediate ideal, it is either here or here, it's either P or the whole ring, as we've proved. Thus, we proved that P is maximal, and therefore, by corollary 6.16, it is a prime ideal. Now, we proved the key lemma. Similar to this one, and that one. an irreducible divides product implies it must divide the factor. From here, uniqueness in so uniqueness in 10.12, the fundamental theorem, follows from lemma 10.11 in a standard way. As uniqueness in the fundamental theorem of arithmetic followed from theorem 1.5, followed from theorem 412.2, and from corollary 10.4. Same thing, this statement suffices for the uniqueness. Thus, I outlined for you theorem 10.12, the fundamental theorem of arithmetic for principal ideal domains. As I proved or outlined the proof that every Euclidean domain is a principal ideal domain, we recovered our previous results about Euclidean domains. The question is whether this new result gives us something more than just the fundamental theorem of arithmetic in Euclidean domains, which we already knew. We already proved it by a different method, but we know the theorem, it was proved. The answer is yes, it does, but it is hard to come up with an example. I know an example. So an example of a PID which is not a Euclidean domain. This is this thing, a plus b 1 plus I square root is write it this way without I, square root is from negative 19 over 2. For some reason not AB, as we are familiar with, but just a little bit different, and B are integers. This is a subring, one can check it, subring of complex numbers. Of, put it this way, subring of C, the field of complex numbers. So you multiply them and add them as complex numbers. It is not entirely easy. It will take a while to prove that this is not Euclidean domain. To prove that this is PID also takes a while, so it is not trivial, neither way is trivial. A very special example, which is in the middle. So the bottom line is that yes, we've got a little bit more than we knew about, or when we proved only the theorem about Euclidean domains. The way to prove is much newer. We proved the theorem about Euclidean domains just directly generalizing from Euclid's more than 2,000-year-old argument. Now, the argument I presented is only some 200 years old. That still leaves a question. There was a blemish, there was an overkill in the proof, so the question arises whether PID is the end of story, whether there are rings which, though integral domains, which have their fundamental theorem of arithmetic but are not PID, and the answer is yes. Our newer argument may be more elegant than Euclid's argument, maybe not, but still our newer argument does not cover all possible arguments to prove that some integral domain is has the fundamental theorem of arithmetic. In the next fragment, I will show you the general picture and say a little bit more about that. Thank you for listening.